the purpose of exercise 10 here is to explore the difference between theory of linear algebra and implementation, numerical implementation of linear algebra. And here we will focus on the determinant. Now, the determinant of a matrix should be 0 if the matrix is singular, meaning if the matrix is reduced rank. All reduced rank matrices have a determinant, in theory, of 0. But it turns out that the determinant is really hard to compute. There's just a lot of flops, floating point operations. It's just a very difficult numerical computation to implement on digital computers. So what that means is that the determinant of singular matrices is not necessarily 0. It's going to be some number. Okay. And what you want to do in this exercise is put the theory to the test. Okay, so create a random square matrix and then reduce the rank of the matrix. Now, you know how to create a matrix with any arbitrary rank. What I would like you to do here is just to set one column to be a multiple of another column. Very simple way to reduce the rank of a matrix. It's not that this is better or worse. It's just that, I like to introduce different methods just to give you some variety. Okay, and then compute the determinant. And we really only care about the magnitude of the determinant. So you can just take the absolute value of the determinant. That just makes the visualization easier. Okay, so then you want to do this a bunch of times in matrices of different sizes. So starting from 3 by 3 matrices up to 30 by 30 matrices. And also we want to repeat this procedure of generating random reduced rank matrices lots and lots of times, 100 times. And that's basically because the determinant of a random matrix can be a random number. We expect it to be 0. Spoiler alert, it's not going to be 0. But just to increase the stability, to make the plot look a little bit nicer, you generate 100 random matrices, 100 random reduced rank matrices for each of these matrix sizes, and then we will average the absolute value of the determinants together and then make a plot. Now, the theory of linear algebra tells us that all of these determinants should be 0. Here I'm plotting the log of the determinant. In fact, this should be errors. These should all be NaNs because you cannot take the log of 0. So the fact that we are even getting a valid result here tells us that something is amiss. The theory doesn't work in practice the way that it should. Again, that's not because linear algebra theory is wrong. It's just because computing the determinant, especially of large matrices, is so numerically difficult that the rounding errors get larger and larger. They start to accumulate and they start to grow. So here you see what this looks like. So here is a variable for the sizes of the matrices to go from 3 by 3 up to 30 by 30, repeating over 100 iterations. And here you can see the double for loop. So here what I do is create a random numbers matrix of size n by n, so square matrices, and then I set the first column to equal the second column. So this guarantees that we will reduce the rank by 1. So when n is 24, then we have a 24 by 24 matrix and a rank of 23. And then I compute the determinant, take its absolute value, and just average all of those together. You can see here, I'm plotting them together. So I chose to plot this in terms of the total number of matrix elements. You can also plot it in terms of the total number of, or the size, number of rows, or the number of columns. It's also fine, just a plotting choice here. I think it looks a little bit cleaner. I think it's a little easier to see what's going on when you plot this on the x-axis. Yeah, and then here I'm averaging over all the determinants. This is averaging over the repetitions of generating new random matrices for each matrix size. And then I'm taking the log. Again, there's no particular reason why you have to plot the logarithm. It just makes the plot a little bit easier to interpret. It just makes it clear. But the main point is that the determinant of every singular matrix is supposed to be 0. In practice, it can be 0 for very small matrices, especially if they are integer matrices. But the larger the matrices get, the less likely they will be to have a determinant of 0 if they are indeed singular. The main point, or the main practical take home from this exercise is that if you are trying to determine whether a matrix is singular, the determinant test is not the right one to use. There's many other methods like counting the number of singular values, computing the condition number of the matrix. I will introduce you to those methods in later chapters.